Hello and welcome. Today I want to talk about change. Change in terms of physicality. So, a change can happen because of various reasons. Maybe you push a pen from your table and it goes down to the ground just because at the ground it has more stability in terms of potential. So potential energy is high at when your pen is at the table, and it will drop down to zero when it will touch the ground because potential energy is mgh. This is one kind of change. When you push something, when you put an effort, you either push or pull things. Essentially, when you apply force. But I again want to narrow down today's conversation to change at equilibrium when there is no external force applied. Let's say you have a glass of water and if we go to the molecular detail, what happens that water molecules present in the glass, they have kinetic energy. Kinetic energy is nothing but a manifestation of temperature. So, as you increase the temperature of any system, their kinetic energy would increase, and as you decrease the temperature of any system, their kinetic energy would decrease. So, water molecules, let's say at 25 degrees centigrade, which is the room temperature, they have certain kinetic energy. These water molecules are doing random walk because of their thermal energy or kinetic energy. As you increase the temperature, their kinetic energy will increase more, and eventually at higher temperature they'll go apart and they'll keep on flying in the air, or it will leave your vessel and it will go in the air. So more the kinetic energy at higher temperature will essentially provide enough energy to escape that intermolecular interactions. Like all water molecules at 25 degrees centigrade, for reference if we talk about, they have some interaction among them, and these interactions are mainly hydrogen bonding, because oxygen has some high electronegativity and hydrogen has lower electronegativity. So oxygen has essentially a partial negative charge on it, and hydrogen has a partial positive charge on it. And because of this partial positive, partial negative charge present across the water molecules, they are bonded by hydrogen bonding. So every water molecule is almost bond to around 3 to 3.5 other water molecules on an average, and these interactions keep on forming and keep on breaking because of their kinetic energy, and they keep on doing random dance in the vessel. As you increase the temperature, they get more energy to go here and there, and then they keep on losing their interactions because they have higher kinetic energy, and eventually they'll start these hydrogen bond interactions will not remain sufficient at higher temperature, and as other kinetic energy dominates, and they leave apart. And when we decrease the temperature, essentially they come near to each other and freezes and forms ice. So ice has lower density as compared to water, because water shrinks upon melting and it expands when we freeze it. Now this is the concept of water. let's suppose there is a molecule in your water. Let's assume there is a protein molecule in the water. So protein molecule is nothing but a stretch of amino acids connected with each other by covalent bond. And these amino acids are of different types. Some are hydrophobic, some are hydrophilic. Hydrophobic amino acids tend to remain together away from water because they have non-polar side chains, mainly tryptophan, tyrosine, phenylalanine, and all these hydrophobic amino acids. So what happens that these hydrophobic, when protein folds, the hydrophobic amino acids, they go in the they are buried upon folding, and hydrophilic amino acids are generally present on the surface, and they are in a close interaction with the water molecules. Now the topic that I want to introduce today is this, that how the dynamics of water molecules, that kinetic energy of water molecules, that water molecules keep on moving, how do the dynamics of water molecules, means solvent dynamics, could potentially affect the dynamics of protein molecules itself. So when I say dynamics of protein molecule, I essentially talk about their movement in various time scale. So one thing is very clear, that if a molecule is dipped in a solvent like water, then first experience that a protein molecule would face is that these water molecules keep on going here and there. They keep on hitting protein, like randomly moving water molecules. They always have a tendency to kick other molecules. So let's say here it's protein molecules. So protein molecules will get kicked by water molecules, and getting kicked around and moving here and there. So these water molecules will essentially make protein to do some Brownian motion, and that's the one time scale in which this protein should originate. So this time scale is in the, let's say, millisecond time scale. And when I say I need to give it, so for a typical protein we have this diffusion coefficient of a typical protein is in the range of 40 micrometer square per second. So they cover 40 micrometer square area per second, every second. So this is the total diffusion of water molecules, diffusion of protein molecules in the water. Second kind of change that protein molecules experience is their internal motion. So let's say we have multiple covalent bonds. So amino acids are linked together by covalent bonds, and they have some degree of freedom, so they will show some change here. Also the side chains also show a flip-flop. Even protein molecules show higher order movement of let's say two domains which are attached to each other. They will show some dynamics out there. Also because of thermal energy, we can think of bond vibration. Bond molecule, bond is nothing but an interaction by which two atoms are held together, and these bonds can be covalent bond through which amino acids are attached to each other, and it can be non-covalent bond through which different amino acids are adhered to each other. So because of temperature there will be bond vibration as well. Now recently some people have observed that all these motion of protein molecules, internal motion and external motion comprise of bond vibration, side chain rotation, some degree of freedom among covalent bond, the peptide bond, and also the larger domain motion, and these things happen in sub microsecond to sub millisecond time scale. Particularly this microsecond time domain is important because this dynamics of protein in microsecond time scale is important to perform various activity inside the cell. So proteins, if we simply freeze the protein, let's say you make the protein very non-plastic, let's say by formaldehyde or something, then it will not be able to perform any function. So to perform a function, protein has to keep on doing this breathing motion or dynamics. People have recently found that this protein dynamics is very well correlated with the dynamics of water in the surrounding. So the water molecules present in the surrounding of the protein, they have certain motion because of thermal energy and all. So there are two kind of water molecules which are present around the protein. So as I said that on the surface generally we have hydrophilic amino acids. On the surface of protein we have hydrophilic amino acids. So there will be protein, and when I say hydrophilic it means it will interact with water. Reason is very simple, that hydrophilic amino acids are polar amino acids, they have polar side chain, and hence they are likely to interact with water molecules. So the water molecules generally form 5 to 10, about 15 angstrom layer of water around the protein, and these are called hydration shell. The protein has its own hydration shell. So wherever protein will move, this water molecules present in hydration shell, they will also move. So that's why effective radius of protein molecule, if we talk about hydrodynamic radius, it includes the dimension of protein as well as the dimension of water molecules present in hydration layer. Second kind of water molecules which are around the hydration shell of protein molecules, and they are present everywhere. And when they and they also keep on doing this dynamics, but essentially they are not in close interaction with the protein, particularly the hydrophilic amino acids present on the surface. Now people have observed that so it's very natural that the water molecules present in hydration shell, since they are in close interaction with the protein, they will not show fast dynamics. So hydration shell water molecules show slow dynamics, and water molecules present outside the hydration shell of protein, they show some faster dynamics. And people have found that the water dynamics of the hydration shell is correlated with the protein dynamics in slower time scale, and water dynamics in the bulk water, which are present all around in lesser interaction with the protein and more free and having more degree of freedom, they are correlated with the faster dynamics of protein. So essentially the solvent has a role on uh, uh, protein dynamics, either diffusion or internal motion of the protein. After that, one natural question that comes up, that how are, from first question is from where protein molecules belong. They belong to cell. They exist inside the cell. And do we have similar water molecules in the cytoplasm as compared to water molecules that we have in the buffer solution, or let's say in a glass of water? Definitely not, because in a glass of water or in a buffer solution in which protein is dissolved, the water concentration is around 55.5 molar, whereas inside the cell we have of course a lesser concentration of water. It's 70%, so it will be around 35-36 molar. Second thing, these water molecules are not the only thing that present in the cytoplasm. The rest 30% are, let's say, we have a very high concentration of macromolecules, 2 to 300 milligram per ml micromolecular concentration is there in the cytoplasm, and these macromolecules can be carbohydrate, these can be protein, lipids and all. Also we have lots of sugars dissolved in the cytoplasm, and these sugars are something who make the cytoplasm viscous. We have other ions as well. We have some reducing environment in the cytoplasm. So one factor is viscosity, another factor is this molecular crowding, and these things are likely to affect the conformational dynamics as well as the higher scale diffusional dynamics of the protein. Now, if we can think that how can, so I'll just finish it as light is gone. So that is the only purpose I make video, because after setting up the experiment, light of this room is not working, so I generally call the electrician and see I got the call. So, and then I make the video. I'll talk in the next video how cytoplasmic concentration could potentially affect the protein dynamics. Hello. So, but before I start, I would like to talk a little about cytoplasm. When I say cytoplasm, what do I really mean by cytoplasm? Cytoplasm is water with sugar, carbohydrate, protein, lipid, fat, some ions, and all of these are naturally selected. That is important. So what do I mean by naturally selected? So when I say it's naturally selected, I essentially mean that everything present in the cell, they have some function, they have some role. If they wouldn't have a role, they would have been in the cell. So the idea is, why am I saying this? Because that is the whole concept of natural selection. That anything which is not necessary, that will be thrown out by the nature. So we, as a life form, we cannot afford to keep something that is not necessary for us. Of course, in the longer time scale I'm talking about. So today also, we have lots of things that are not in use, but in future they will be vanished. So whatever we have today in the cytoplasm, they have some role. This angle makes the argument even interesting. Why? Because it means that whatever function that a protein molecule performs, they have been selected to perform in the cytoplasmic environment, not in the entirely buffer solution environment. Okay, then the question is, how can these environment potentially affect the conformational dynamics or diffusion of the molecule? So one way to think about, that since cytoplasm is more viscous, they are likely to affect the kinetics, because we all know what did great Kramer said. Kramer said that, we all know the collisional theory. For a reaction to happen, two things have to come together. And how do they come together? Like if a reaction, for a general reaction, like let's consider a reaction A plus B gives you C plus D. Now for this reaction to happen, first of all, A and B, these two molecules have to come together. And how would they come together? They don't know, they don't have memory. Like A don't know that they have to meet B and perform some sort of reaction. Then generally they keep on diffusing in the solvent, and during the diffusion there's a fair chance that they'll meet, A and B molecule will meet. And when they meet, if they meet in a proper orientation, and that meeting will be a sort of collision. It will not be a nice meeting like hi and hello. It will be a sort of collision. So, when two molecules, okay, so when two molecules meet with each other, it will essentially a boom, collision. But if every collision will not lead to a reaction and gives you a product C plus D. It has to be an effective collision. And what does effective collision would mean? That they should collide in a proper orientation. If they will collide in this way, then only reaction will be accomplished. Otherwise it will go here, there and there and there. Now, the question is, what determines this collision of molecules? So one way to look at it is this, that something that affects diffusion, the same thing will affect the collision, intensity of collision. Okay. So now the idea is, what is it that affects this collision? So, so to understand this, simply we need to understand diffusional theory. And who gave the theory of diffusion? So, of course, the Brownian motion was discovered by Robert Brown, that molecules keep on doing random walk in the water molecules, only because they have some sort of jiggling motion because of water molecules hitting them, and they keep on moving. And at the end, Stokes and Einstein both independently gave this theory that this dynamics of this diffusional dynamics essentially depends on two things. One is the thermal energy. So thermal energy is kBT. So kB is the Boltzmann constant. So anywhere, this is like rule of thumb, the thermal energy is kBT, Boltzmann constant, into temperature, because temperature gives you the thermal energy, which is essentially a measurement of kinetic energy. So more the kinetic energy of a molecule, more the diffusion, of course. That is one thing. Second thing it depends on is the viscosity. Of course, inversely. So diffusion coefficient of a molecule directly proportional to the thermal energy and inversely proportional to the frictional coefficient, and frictional coefficient is 6 pi eta r. So eta is the viscosity of solution of solvent in which protein molecules are moving, or any molecules are moving, and r is the hydrodynamic radius of the molecule. It's not the radius of only molecule, it is the hydrodynamic radius of the molecule. As I said, that protein molecule has a covering of water molecules around it, and they are considered as their water hydration shell, and so we consider that while calculating this hydration hydrodynamic radius. Now the question is, diffusional dynamics will depend on thermal energy in a directly proportional way and inversely proportional to the frictional coefficient, which essentially is the 6 pi eta r viscosity in hydrogen. So more hydrodynamic radius means fatter the molecule. Fatter the molecule, slower will be their movement. Okay, so diffusion will essentially govern the rate kinetics. In this, dependence on viscosity is essentially given by Cramer. So hence Cramer said that more the viscosity, lesser this dynamics. Okay. I am not seeing this. So that is the one criteria on which reaction will also depend. So since reaction is diffusion limited, and since reaction is diffusion limited, it will depend on the criteria that affects diffusion. And what affects diffusion? Diffusion is affected by viscosity and hydrodynamic radius of the molecule. If we have an agreement on that, then we clearly get an idea that inside the cytoplasm there is more viscosity, hence the conformational dynamics, kinetics of conformational dynamics should be certainly different inside the cytoplasm as compared to the what we get in the buffer solution. Now, second thing, is this. That how does it affect the thermodynamics of the the reaction, maybe internal dynamics reaction. So when we say, can we consider internal dynamics as a reaction? Well, we should not. But when we use a probe, that if that probe is some, to monitor any physical phenomena, we use some probe, some method to understand it. So the method that we have now is a reaction, and that reaction should have a dependence, so definitely. So to understand how can cellular environment affect the any reaction, we have to understand the concept of thermodynamic potential. So which says which says that when a reaction happens, so we have reactant. Both reactant form some intermittent structure that we call transition, transition state, and then it forms some product. Now the free energy of any component does not solely depend on its own free energy, it also depends on the interacting partner. So let's see, if a protein molecule is in water, then they do not essentially have any interacting partner, because the size of water molecule is around 18 Dalton. Size of protein molecule is around, let's say if it is smallest protein, it is around 10 kilodalton. So about 8-10 times larger. So not 8, so 18 to like 1000 times larger, 500 to 1000 times larger. 1000 times larger is a lot. So the whole idea is this. That so whole idea is this, that if reactant or transition state or product, if they interact with something else, that interaction will, what is interaction? Interactions is some electronic or electron proton when electron or electron proton, they have some force in it which has essentially changes the free energy of a molecule. So if, let's say if we have protein molecule and in cytoplasm, some other carbohydrate or protein molecules came by and they just they are surrounded in its environment. So first effect will be an entropic effect, that these molecules cannot access the volume which is already occupied by other molecules present in the cytoplasm, and these other molecules can be carbohydrate or protein. So water, these protein molecules will have certainly lesser entropy in the cytoplasm as compared to a buffer solution, and this lesser entropy will affect its free energy, because free energy is H minus Ts, enthalpy minus Ts. So free energy is nothing but a compensation of enthalpy loss or gain, or entropy loss or gain. So if entropy will be different, it will certainly affect its affect its thermodynamics, as well as if they have some sort of interaction. Let's say, a carbohydrate molecule or a protein molecule had come and interacted with my protein of interest and released some heat. Let's say if it is an attractive interaction, so it will lose some heat, and lose some heat will essentially mean that enthalpy will be reduced, and this reduction in enthalpy would again change the free energy. So today I explained there are two ways by which cytoplasmic environment or intracellular environment can potentially affect the protein behavior in terms of change, in terms of dynamics. So diffusional dynamics will be affected by viscosity as per the Stokes-Einstein equation. Diffusion coefficient is kBT divided by 6 pi eta r. Internal dynamics is also dependent on viscosity because it is a diffusional limited dynamics. And thermodynamics of the protein, either in terms of internal dynamics or in terms of doing any sort of reaction, protein folding reaction, conformational change reaction, it will be affected. A reaction will be thermodynamically affected if the effect of cytoplasmic environment in terms of enthalpy change and entropy change will be different on reactant, transition state and product. Let's say if we have effect of cytoplasmic environment, if we have same effect of cytoplasmic environment on reactant, transition state and product, then essentially your free energy landscape will not change. Free energy landscape will change only when the cytoplasmic environment changes the free energy of reactant, transition state and product differently. Thank you.